Hello and welcome to this next lecture in the course, which is on virtual environments. So starting here at the beginning of this section. Again, Abdul and I are on the course. Of course, I'm doing the lectures and Abdul's doing the tutorials, as you know. So starting up then, talking about virtual environments. Well, I wanted to mention virtual environments in this lecture because there are two meanings really to the term virtual environments on this course. The first one has to do with what we've been doing really with LabVIEW, and we've been creating these virtual instruments, haven't we? I mean, I know that the actual subroutines, if you like, that they create in LabVIEW are called virtual instruments, but what you can actually do with the software and what's designed for, of course, is creating these virtual instruments, and that's what they had in mind when they first designed the software. So a virtual sort of laboratory instrument, I guess you could say. And so here we've got a virtual multimeter down the bottom here. And here's the real physical multimeter that we've got on the shelf in the laboratory. So we can use LabVIEW to create these virtual instruments. And the advantages there, of course, is that we get more versatility because the person who creates the virtual instrument can create it with any kind of options he wants on it, or they want on it. And inputs, outputs, and more flexibility and versatility, I think you could say. And of course, you've got less space requirements. You don't have to have these physical instruments all over the lab. You can just have one computer with a suitable card and then implement different instruments on the screen as you want them. And that's going to mean you can have reduced costs, of course, because you won't have to keep buying this hardware all the time. So that's the example that's the first concept of what a virtual environment is on this course. The second concept is a virtual environment where you have powerful 3D graphics, such as ray tracing methods, for generating realistic or photorealistic images of objects or scenes. And these can be very high quality, so they can resemble photographs that be taken of objects or scenes. You can see here, you can get all the reflections quite well with a technique like ray tracing. And I'll talk a bit later about how ray tracing actually works. You can see that in this saucepan here, we've got all sorts of complex interreflections from various objects in the room. This is all a virtual environment. None of this exists in the real world. And I think it's quite a nice little demonstration, really. You can apply bitmaps to various surfaces to give different types of material or appearance, also kinds of reflections. And the original idea I had some years ago with all this was that you could use this kind of virtual reality software and approaches, methodologies that we're going to talk about, to create photorealistic images of maybe components that you want to sell and manufacture and sell. So this is your concept of what the final component looks like. And then, you could be doing this, you could be manufacturing in Asia, say, and designing in Europe. So then the idea was that if that's the case, that when you start actually making the part, you could use cameras and special lighting and visualize what the part actually looked like when it comes off the end of the production line. And then the idea I had was, how does that compare with the virtual version of the part you had early on when you were first imagining it? So, that's where machine vision comes in. It allows you to generate those real images, actual images of the real part and compare to the simulation. So that was how they all fitted together for me with this idea of, of machine vision and the virtual environments. So what can you do with virtual prototyping? Well, this has been used quite a lot of industry, of course, and we employ something like ray tracing to give the designer a good idea of what the final aesthetics of a product can look like. And of course, you don't need to spend time and money on manufacturing the environment to put the product into. So, quite often a nice new car, this is a few years old actually, this design, I guess, but this nice flashy car will look good against a scruffy background. So rather than taking it somewhere where you've got an old building in the background, you can just generate a virtual one. So none of this actually exists. This is all just a visualization in the computer. And virtual prototyping is, as I say, when you have manufacture a product, and you can generate, say, you can generate a solid model or even a surface model if you want to, and then use your ray tracing and other techniques to generate the photorealistic image of the object, and in various environments and positions to check function and aesthetics before manufacture. So you can check in the virtual prototyping idea, you can also check the mechanisms work in various ways according to how you expect them to, according to how they've been designed in the CAD system. and then you can check the aesthetics to see whether it's got the appearance you want it to have. So this diagram is meant to be showing the 3D modelling in the CAD system, generating the solid model of the part, and then applying the rendering in 3D to give it a sort of realistic appearance in the computer. And quite a big application area for this kind of technology is things like car interiors. And so when you're trying to create a vehicle interior, you need really attention to detail for this. I mean, here, this was quite a nice visualization. It was done in France, I think. And we got the stitches in the grain of the leather, stitches and the grain in the leather here. You can see we've got the reflections of the various objects like the dash in the car and pattern of the speaker covers, as it says. You know, this is the kind of thing that might affect the overall aesthetics of the design. So I suppose there's two parts to this. Maybe the designers in the very early stage of the concept of the car can try different interiors to see what they think looks better and what they really appeals to them. And they need to worry about interreflections and photorealism to get a really good idea what the final vehicle is going to be like to be in. And then once the thing's been designed and manufactured, I guess, the potential customers can come in and do a virtual experience of the car before, when they're considering buying, they can actually get into that interior as though they're there. Or they can visualize it, move around, change lights around, and get a really good feel for what the car can offer. And I think that would also help with the marketing of the vehicle. So it's quite a big area. I know that Jaguar has invested heavily in virtual reality for these kind of new areas in automotive. Interior design, of course, and this is a big area. I mean, when I had my kitchen done years ago, I think B&Q did a sort of crude interior design of it and a CAD system of some sort, but it was nothing like as impressive as some systems you see. This one I put in because I thought it was quite interesting how they've got a sheet of glass on top of the table, and you can see that the light is actually passing through the glass. And I'll talk a bit more about that later on, but it's not just reflecting off the surface of objects, you can also do light passing through objects and having various interesting effects. Talking about interesting effects, this is again a virtual scene, but you can see how the interesting interreflections off the surface of this leather couch here is kind of giving it more of a sort of realism, or sort of makes you feel you're there more. There's more texture there. And you've got the light coming through the window with some interesting interreflections. And there are a couple of techniques that you use to produce these kind of images. The first one I'm going to talk about in a minute will be ray tracing. So the light comes in, obviously reflects off various things, and that gives you an impression. There you go. Now, in other applications, it's not just interior design, you can also use it in architecture. And this chap went to Notre Dame in Paris, and he must have done a tremendous amount of study to really get this kind of detail. And you could have argued you should have gone there and take a photo, I guess. But no, this is attention to detail and real love of his art, I suppose. And so you rig up the light sources, you surface, you apply bitmaps to give coloration. What we have done in our lab, done some work on, is the bump map. You remember I talked about bump map from the point of view of photometric stereo. The bump map is a dense array of surface normals. So suppose you're producing an interior where you've got a carpet or maybe some bricks or something. They will have texture in 3D as well as color features, of course. So if you apply this bump map to the surface, then the light reflects off these, according to Lambert's law, off this texture in a sort of more realistic way. You could also apply it to something like this. You could have it reflecting off these stones here and making it look more like actual stone. But that isn't really implemented most of the time in commercial systems. They usually use bitmaps, but there's not much use yet of bump maps. But it's kind of an interesting area that we've pioneered a bit, where you can really make visualizations more realistic by looking at those reflections due to orientation of the surface as well as the actual color of the surface. And this was a firm who did some more modern visualizations. You can also do things like water, of course. You can do any kind of complex light interaction, really. This is more of a modern exterior. Someone's got their own pool, very, very nice, I would say. But you can see the reflections and the transmission of light through the glass, and some quite interesting effects they've got in the ripples down here as well. It's all done in a virtual visualization. Quite a nice effect, I thought, that one. You can do, of course, this on a big scale. Once you've got the CAD model, you can then especially with computation capabilities now with the GPUs, there's nothing stopping you doing virtual walkthroughs and in sort of real-time realistic visualizations, and really as though you're there. And if you combine that with things like Oculus techniques, then you could really have a sort of submerged experience, or immersed, I should say, an immersed experience, immersed in it, as though you're actually there and have it actually true 3D appearance. But it depends on how far you want to take it. Some people are doing that on interiors of factories to make sure they can see what things look like in office layouts and so on. Another application, of course, is teaching, training and instruction. This can be used in the actually, UWE has quite a lot of investment in this. They train radiographers for using those radiation machines that you find in the oncology center in the basement, for example, where they applied cancer treatments with radiation. But you can't use those machines in training because they're too expensive for one reason. So what they did, the UWE, is invest in I think £500,000 in a system which creates a three-dimensional, very realistic actually, because I went to see a demonstration of it, a very realistic three-dimensional visualization on a stage of the cancer treatment machine on full scale. And then you can interact with it with some special glasses which are also active. So the glasses are linked to the illumination model, and then you can sort of look around very impressively, I thought. Look around a thing as though it's really there and interact with it. And this was installed by a company that I dealt with in some teaching related and research related work called Virtalis. Virtalis is a British company who deal with these installations of sort of virtual reality presentations. And there are lots of different technologies which we won't go into here in much depth in this particular lecture, but there are various ways of getting this really impressive three-dimensional visualization rather as though it's actually there, as you can see in this illustration. Some systems require you to wear glasses that are synchronized. It's a bit like three-dimensional cinema, I guess, where you have these special, they use special frequencies of transmission on the lenses, on the glasses that they wear when you go in there. Well, the kind of thing you see in the planetarium, if you see a three-dimensional show they've got in London in the planetarium. Yeah, those kind of things. So, and also when it comes to instruction, something like augmented reality is quite useful, and a company like Rolls-Royce uses this a lot. So engineers put on glasses which transmit into their eyes certain information at various times when they're trying to repair or maintain certain bits of equipment, for example. So rather than having to look in a book, a big paper manual, they get the relevant information about what they're looking at thrown up so they can view it straight away, and they can update logs as well as to what they've done at any time. So it's a sort of an integrated computer augmented reality. Augmented reality is when you're looking at the real scene, but you're getting certain projections of certain graphics added onto it, rather than completely virtual reality where you're completely submerged and immersed in a different environment. And a photorealistic image is what we're going to talk about here a lot. So what is a photorealistic image? Well, it's any image synthesis technique that produces pictures through accurately modeling the propagation of light. So it could be all sorts of different sectors and applications. And the idea is that photorealistic images cannot be distinguished from photographs. Well, I could have had a photograph of this strawberry, and under the right conditions, it would be, the idea is that the photorealistic image would be, couldn't be distinguished from it. Sometimes, by the way, you can use techniques like rendering and ray tracing to produce things that look a little too perfect. I don't know if that's the case with the strawberry, but sometimes it's a little too perfect, and you think, oh, crikey, that can't be real because it's too good, the image. So they might introduce some techniques like noise or whatever to try and eliminate that a bit. But so how are photorealistic images produced? Well, ray tracing is a technique I've been talking about. And that's where you use it for rendering three-dimensional graphics with very complex light interactions, as a general rule. This means you can create pictures full of mirrors, and not that I got any mirrors in this one, but I got doorways, or there's reflections off this hob here, all sorts of reflections, transparent surfaces and shadows, and you can get some pretty stunning results. There's lots on the internet you can find in relation to this. There's lots of bureaus who try to do impressive interiors and so on. You can see some interesting, realistic kind of reflections off the floor there, with that wooden floor there. I think it's quite good. Yeah, and there's various applications. So what is ray tracing? Ray tracing is a relatively easy method to understand and implement, really. It's based on the idea that you can model reflection and refraction by recursively, repeatedly, following the path that light takes as it bounces through an environment. So you're tracing rays. It's not surprising you're tracing rays since it's called ray tracing. And it's good for modelling all these kind of complicated interactions or reflections between objects, as you can see with these spheres are meant to be kind of reflective, complicated patterns there. Now, how does it work? Well, it's so named because it simulates the path the light rays take as they bounce around within the world. They are traced through the scene, as it says. The objective is to determine the colour of each light ray that strikes a view window before reaching the eye or camera, if it was machine vision. If rays are traced starting at their point of origin, the light source, as it says, would, if it was coming from the origin, there would be a lot of light reflections and a lot of light transmissions that you wouldn't need to worry about because you'd never stand a chance of seeing them, really. You could argue like these rays of light are coming from the light source, but you're not seeing them. So calculating these transmissions is, you could argue, a bit of a waste of time. So they use something, they trace back from the camera and only consider the rays that pass through into the camera or the eye. They only consider those rays and see what interactions they had. That's the idea of ray tracing. So you trace the rays back from the camera, back to the light source. So as it says here, so we're saving ourselves wasted effort and tracing only those rays that are guaranteed to hit the view window and reach the eye. Instead of tracing the rays starting at the light source, we trace them backwards, starting at the eye, as I just said. This is what this diagram is meant to be showing. And this is another diagram, probably a slightly better one I've got of that. So yeah, so here we've got the viewpoint. Now this is the view plane, I call it, but you can consider that to be, you know, in the viewpoint you've got a camera, okay? In the camera you've got a sensor, and the sensor, of course, is an array of photosensitive pixels. And that's what this is. It's just that you've moved it forward to see it more clearly. So these corresponds to the pixels in the camera. Now you're tracing back from the camera and you're looking for a light that seems to have come and reflected off an object and eventually can go back to the light source. So the question is, how was that light, when it bounced off the object, because in reality, of course, the light's going the other way, how was it pigment of that light changed by the reflection from various objects? Is the question. That's what you're doing in ray tracing. And of course, you might have a slightly more complicated situation than just one object. And if it's bounced off other objects like the table, then you have to model that. So it could be more than the table, it could be other objects in the scene. So in other words, there might be multiple interreflections from various objects in the scene. And these are modeled as part of the ray tracing modeling. So here we've got a table. We've also got a flower pot, and we get this light reflected. This one here is coming from the light, but that bounced off, so we're not considering that one. But here, the directly reflected light rays going up there, we're going to model that one. And this is a little bit more complicated here, you see, because we traced backwards and found that it's possible to have this combination in this situation. So it is possible the light reflected off the floor here, then off the flower pot, went on to the table, and we finally got a final a bit of light in the viewer situation of the camera or the eye with that. So it's a little bit more complicated and that we can have multiple reflections. Now, these are some old diagrams of the sketches I used to do, and I sort of got sent to put them in for sentimental reasons or traditional reasons, I guess. But how ray tracing works. Now, ray tracers, the important thing to know is they only model specular reflection. And specular reflection, as it shows in this diagram here, is reflection that comes as a mirror. So as you know from mirror type reflection, the angle of incidence is equal to the angle of reflection. These two angles are the same, theta. And if you don't view it exactly along that line, then you're not really going to see the brightness of the light. So if this guy's not going to see that light very well, because he's not actually in the same angle as that reflected beam there. And of course, the other alternative for the way of reflection is diffuse reflection, which is like diffuse reflection like from matte objects, like a sheet of paper, where the light comes down, hits the object, then it's reflected in all directions more or less equally. Okay. And but the thing is, because the ray tracer only uses and considers specular reflection, that can sometimes end up with a rather dark image. So one way in the past has been used to overcome that is just to increase the brightness of the image, really, by a background sort of ambient light component. So that's something that's part of the simple Phong model, which we will talk about in a minute. So here we have a matte surface. Okay, how are we going to model that? Imagine a matte surface. How are we going to model that? Well, I talked before about Lambert's law, and in fact, Lambert's law is a way to model a matte surface, to model a diffuse reflection. So for a matte surface such as paper, the reflection is diffuse. Light is reflected in all directions, as it says there, and that can be modelled using Lambert's law, as I mentioned a few times. So here we've got a light source, intensity II, and then it's coming down here, and it's hitting this surface here. That's the surface normal. That's the vector. It's normal to the surface at that point. And then the angle between the light, what we call the lighting vector, where the light is, and the surface normal, is theta. Lambert's law says that the intensity of the diffuse reflection will emerge, I equals I, which is the intensity of the light source, times a constant, kd, times the cosine of the angle between the surface normal and the lighting vector. In other words, it's only dependent on the orientation of the surface at that point. That's what it's saying. And this is a reasonable assumption. Actually, it's extremely useful, Lambert's law, for all the kind of work that we've been doing over the years. It's very often suitable, because a lot of the time, many surfaces do sort of reflect in a diffuse way, or at least there's a large diffuse component, you could argue. But so that's diffuse reflection there, and that's modelling it using Lambert's law. One thing that's worth mentioning is that in this model, you notice that the position of the viewer is not actually incorporated in the model. You normally assume, a lot of the time, that the view would actually be from above, because typically if you're trying to view something with a camera, like in photometric stereo, you've got some lights and a surface and a camera, you remember. The camera is going to be above the surface, isn't it? But it's not actually part of the model. The next thing is, how do we model a specular or shiny surface? And this could be a shiny surface such as that you see on a snooker ball. Okay, so the reflection from that kind of object is mirror-like, and we model that using Phong's lighting model. Now this is again a little schematic showing the intensity again is II. The angle again, the light's coming down from an angle of theta again, and if it's a specular reflection, as we just said for the rule of mirror-type reflection, the angle of reflection is going to be equal to the angle of incidence. So most of the lights, if it's very specular, sorry, that should say specular there. I'll change that before I put that onto Blackboard for you. I meant to put specular there. So because it's specular, most of the light's going to be reflected off along this line. Okay. Now the viewer, so it does. In other words, it does depend in this case. I mean, it's highly dependent on the angle of view. The apparent intensity does depend on the angle at which you view it. Okay, for this kind of specular reflection. So what we're saying here is that the perceived intensity we're going to see I equals the intensity of the source times a constant again, times cosine of omega and to the power of n. Now this is the cosines are to the power of n. So what we got here is something which is highly dependent on the angle of view. As this angle changes, omega, it's going to really change the apparent intensity of this specular reflection. Okay, and interestingly, like if you had a snooker ball, you can imagine if you had a light shining onto a snooker ball, you'd get a highlight in terms of a circular highlight, wouldn't you, with the light on the ball. And the specularity of the ball is really controlled by this value n, this parameter n, because as that varies, the size of the specular highlight on the ball will also vary. You can imagine a more diffuse ball will have a larger specular highlight, and a very, very shiny one would have a smaller specular highlight. It's worth reading around this on the internet a bit, find out a little bit in addition to these notes I'm giving you, a little bit about Phong models, about the Phong lighting model. But it's a nice simple way to model specular reflection when you're trying to produce a photorealistic image. So then the Phong lighting model, the overall model then combines those two things we just talked about along with the ambient component. So the actual intensity we're going to see, the point equals this ambient component, the ambient light and the ambient constant, plus this diffuse component with Lambert's law, just talked about, plus the specular component which I just mentioned. And that's the overall Phong lighting model. It's a fairly simple sort of There are more complicated ones, but it's a nice one to start with, to think about how you can actually do this kind of implementation of ray tracing to give you photorealistic images. So another thing I should mention while we're here is radiosity. Now, I will put another document onto Blackboard to give you a little bit more background on radiosity and what's involved. It's quite a big subject, and a lot of CAD systems like Rhino and 3D Studio Max that works with AutoCAD incorporates this kind of technology, but they don't often tell you the maths behind it, probably because they don't want you to start doing it yourself. But so you can't sometimes get into the nuts and bolts of how they're doing it, but they just allow you to control the effects of it. But what radiosity is, as it says here, radiosity assumes that any light that hits a surface is reflected back into the scene. Everything is considered to be a potential source of indirect light. Okay, that's quite important. So, you know, the distinction between light source and objects breaks down with radiosity, because the objects can themselves be light sources due to the fact that the light's reflected off them. So with radiosity, when we are considering how much light is reaching any part of the scene, we must take care, as it says, to add up the light from all possible sources. For example, we have here some fluorescent tubes in this rendering visualization scene. Now the fluorescent tubes, the light's coming down. We get more of a ray tracing situation. We're just looking at the light directly reflected from the objects, and then we're seeing this kind of image. And you can see again it's a little bit dark. Certain parts there's not so much light reflected, because it's only direct reflection we're really considering here. But if we start thinking about, okay, there's objects in the scene, like the light comes down and hits the floor, then the floor acts as an emitter itself and reflects a certain amount of light back onto the ceiling. And the walls and every object in the scene to some extent reflects, you know, ambient light around. So by the time we've done all that, worked all that out, we find that this is probably more of a realistic scene. This is probably what it would be more like if you were there. You've got a little bit more in terms of diffuse light. This gives you a more realistic solution to making the image brighter, rather than just putting a constant, you know, increasing the background brightness with the ambient component, which is what that does. With this, you've got this more realistic interreflection of diffuse light, which gives you more like what you actually see. Now, if you go into a typical room, you know, most of the light's reflected around from the walls, isn't it, really? So this is more like the kind of thing you're doing with this. So as it says here, it can eliminate the need for the ambient component mentioned above, and can produce very realistic images. I mean, this is just an example. You can get very, very realistic images with that radiosity. However, it can also be computationally intensive. If you imagine with this, you know, with ray tracing, we said we're only considering these mirror type reflections really, and we're only looking at ones that actually go into the camera. Okay, but with this, light might come down, hit the wall, it might hit it. You can imagine it could bounce all over the place. It might eventually end up in the camera to some extent, a little bit of it. But there are literally millions of possible light reflections. There's a vast number of light reflections that are possible when you're not considering indirect reflections that don't necessarily trace directly back to the camera. So the amount of computation required to implement radiosity can be very high. But this is not really that much of a problem nowadays, perhaps, because we've got these GPUs that gamers have been getting going for us. And really, I bought an RTX one for doing some deep learning, and they're very impressive what a number crunching you can do with these GPUs. And so now we've got relatively cheap means of high power computation with our top end PCs, which are, you know, high quality GPUs. So we can do number crunching. So radiosity is not that impossible. I mean, certainly you can do it for static scenes like this. We can probably even do it for dynamic scenes, because computing's coming on all the time, and these kind of techniques, which offer more realism, are more favoured really a lot of the time for doing realistic interior visualizations. Refraction then. Now it's not just reflection, we can also have refraction. Do you remember I showed you near the beginning that sheet of glass on top of the table, a coffee table? So refraction, so just as shadows and reflection are easily handled, so is refraction. But to handle refraction, we need to consider what happens when a ray passes through a partially or fully transparent object. Okay? Now the direction of a ray of light changes when it passes through an interface of two materials with different refractive indices. Okay, so along comes this ray of light here. It's hitting this object here, but this object's got a different, maybe this is air and this is glass or something. It's got a different refractive index. Slowed it down a little bit. There's a reason why it changed its orientation. You can see that the angle here is different. It's smaller than that angle. We've got a refracted ray. But there's no real problem modeling that in ray tracing. That's something we can do. This is physics, of course, and we can apply laws of physics in our simulation of rays. Not a problem, really. So it's not just simply getting that refraction from that object. We also have all sorts of various reflections. So this diagram, the idea of this diagram, it shows more of a general lighting model. So in comes the light. We get some reflection off the surface. Now this is a glass, it's meant to be a glass block of glass here. So we probably get quite a lot of reflection on a specular type of reflection there. We also get some diffuse reflection. Okay. Reflecting all over in all different directions. Now, because this is glass, it will have a different refractive index, and the light will travel through it more slowly, so it bends towards the normal. And here we have the refraction occurring, a change in direction of the light. A certain amount of absorption will occur inside the glass block, which will see light traveling off at various angles, and some of that light will pass through this barrier back into the air again, which will be more diffraction going on there, I guess. When the ray of light hits the external surface here, again, a certain amount will suffer internal reflection, reflected back inside the glass block. But probably the majority of it will actually be transmitted. Again, refraction occurs when it passes through this boundary from the glass back into the air. It again speeds up, which leads to, because it's going at an angle, it leads to a refraction angle change with the transmitted light coming out of there. So that shows from the physics point of view, from various interactions of light rays with objects that you can have. Now, I thought this image was good because it really is pretty stunning, I think, really. But it shows you the kind of thing you can do with ray tracing. Now, in ray tracing software, there's something called POVray, which was written in C. And the great thing about this, I mean, a lot of people I know have used it for research to some extent. But because it's written in C, and it's public domain, you can use it in research a lot, and you've got complete flexibility with what you do with it, of course. And you can do all sorts of impressive reflections and refractions and diffusions, and you can see this is looking very, very realistic. Whether this is a case of getting too good and not looking realistic, it's a little too perfect, I'm not sure. But it's certainly pretty impressive, I think, showing you the kind of things you can do with something like POVray. The disadvantage of using something like that, perhaps, is unless you're a programmer, it may be a little tricky to make the suitable modifications and get the thing running in the way you want, because it's C. Programming is a bit of a subject in itself. It is written in C. So depending on what you want to do with something like ray tracing and photorealism, you can go from, if you're trying to use it more for a research point of view, you probably want POVray. If you're a user who just want to visualize things for clients, maybe things that you want to, interiors that you want to, you can get versions of AutoCAD that work for architecture and the built environment. So you probably use some 3D Studio Max or something like that and create some various impressive interiors you could give to clients if you're trying to sell some design work. And that would be the way to go there. So students run them in projects and things like Rhino and 3D Studio Max and produce some very impressive results I've seen over the years as well, to be honest. And just one last note I wanted to make is that one thing I do say quite a lot in the course is that I talk about skin actually, because we do a lot of work on the skin analyzer, and I say skin can really change in appearance depending on the lighting angle, okay, because it's a texture there. You've got this 3D texture as well, and it's not just skin though. All sorts of scenes can vary dramatically depending on the lighting angle. So someone has generated this scene here, and outdoor scene, and got all these people in it, and then once they've generated the scene, they just change the lighting a little bit. The sky and the lights have been changed around, and you can see the dramatic change in the apparent appearance of this scene just by changing the lighting angles. So that's something you can do in not just in these kind of scenes, but again, if you're looking at something like interior design, you can move around spotlights and ambient lights and coloured lights. And I mean, I did this once for few years ago, we were moving a laboratory. We were moving into a new laboratory in the DuPont building, actually. This was some years ago. And we had quite a lot of space, and we had layout for ideas of laying computers out and experimental rigs on quite a big scale. And I created it in 3D Studio, actually. And I was getting quite carried away with it. You know, I was putting in bookcases and putting bitmaps of wooden effects on bookcases. I was moving lights all over the place. So one problem with this kind of thing is you can get a bit carried away and spend a tremendous amount of time on trying to get it exactly right or trying to improve it all the time. But really all you need to do is a lot of the time, and this is an artistic thing, but a lot of the time for interior layouts, and you're just trying to think about the logistics of it and whether there's enough space for what you want to do. So a lot of the time, people, I mean, when we moved into the new building in the Hewlett-Packard T block, which is where I am now, in T block, again, they weren't even doing that kind of visualization much. I didn't see much evidence of that. I think they did 1 or 2 walkthroughs, but a lot of the documents that they showed us were just 2-dimensional drawings, because we want to get the basic information across. So whether you get into these kind of techniques for virtual reality and virtual prototyping probably depends entirely on who you're generating the data for and what kind of information they need, whether you're trying to wow a client or whether you're just trying to tell somebody some basic information in relation to their space available. But it is an exciting technology, and it is quite amazing what you can do with some of these techniques, and it is a lot of future for virtual visualizations. I think, especially with something like COVID coming along and more social distancing, remote visualizations of better quality and more immersive experiences are probably going to be more and more popular because, you can't necessarily get in there and right in the middle of everything now, as you know, to do the things you want to do. You do things remotely more, I think. So I hope that was of interest. That's virtual environments for this lecture. I hope you found that useful. I'll see you all next week.